In this video, we're going to talk about light. This is the most important subject of the whole visual arts, because light, as well as air, is something that we only notice when we miss it. But for us, it isn't only important because it will allow us to see an artwork, but also because we will be able to show what we will decide to represent inside of it. Here, we're going to see two theories about it. In particular, we're going to see the one that sees the light as an electromagnetic waves flux, and the one that sees it as a corpuscular flux. So, first, we're going to define the electromagnetic wave, the electromagnetic spectrum, and the electromagnetic band. Then, we will define what's an electromagnetic waves flux, and in particular, what's a white light flux. We will see the three ways that the light has to interact with objects: the reflection, the refraction, and the diffraction. We're going to talk about opacity and transparency. We're going to see how the external surface finishing and shape of an object will influence the reflection and the refraction of the light flux. And at the end, we will introduce the concept of caustic effects. Don't worry, we won't go too deep, so it will be easy to follow. In both the theories that we're going to see now, the light flux is represented as a group of basic elements called photons, and they are all traveling in the same direction. In the corpuscular theory, the photon is considered to be a particle called precisely corpuscle, which has a mass. Therefore, it's subject to all the physical laws about mass. In the electromagnetic theory, the photon is seen as an electromagnetic wave. Therefore, it's subject to all the physical laws about electromagnetic waves. We're going to consider these two theories because, according on how we tickle it, sometimes the photon shows itself as a particle and some other time as an electromagnetic wave. In both cases, the photon is an energy carrier that moves the energy from one place to another. Let's focus now on the photon seen as an electromagnetic wave. By our point of view, an electromagnetic wave is something which has the shape of a wave. It's characterized by its intensity, its wavelength, and the carried energy. Actually, the energy carried depends on the first two parameters. So, the energy carried by an electromagnetic wave will increase if the intensity of the wave increases, and it will decrease if the intensity of the wave decreases. It will increase if the wavelengths decrease, and it will decrease if the wavelengths increase. By the physical point of view, it's the wavelength that characterizes the electromagnetic waves. According with their wavelengths, they can be called in different ways. We will call the totality of the electromagnetic waves, starting from those with the largest wavelengths up to those with the smallest one, electromagnetic spectrum. We will call electromagnetic band a portion of the electromagnetic spectrum between two different wavelengths. To make it simple, we will divide the electromagnetic spectrum in three macro bands. The one above 100 micrometers with the largest wavelength that we will call the broadcast band. In the middle between 100 micrometers and 50 nanometers, we will have the natural light band. And at the end, with a very small wavelength below 50 nanometers, there is what we will call the dangerous band. Fortunately for us, these waves are not naturally available on the Earth, so we don't have to care about them. For painting, we don't really need to talk about the broadcast band. So at the end, we will only focus on the natural light band. The natural light band itself is composed by three different types of wave. The waves with the largest wavelength between 700 nanometers and 100 micrometers that belong to the infrared band. The waves with the smallest wavelengths between 380 nanometers and 50 nanometers belong to the ultraviolet band, and the waves in the middle between 380 nanometers and 700 nanometers that belong to the visible band. By our point of view, we don't really need to talk about the infrared band because they are not visible, and in the natural light band they carry the lowest quantity of energy. We're going to talk about the ultraviolet band because, although we still can't see them, inside the natural light, these waves carry the highest content of energy, and they can be dangerous for our paintings. We definitely need to talk about the visible band because these are the only waves that we can actually see. To make an example on how the ultraviolet waves can be dangerous, we can see what happened to the people with a very white skin when they lie on the beach under a very strong sun without any protection. We can somehow prevent these problems by choosing the right materials before we do our painting. Let's introduce now the electromagnetic flux. An electromagnetic flux is a group of electromagnetic waves that belong to a specific band going in a specific direction. In particular, we will call white light flux a homogeneous group of waves that belong to the visible band going in a specific direction. We will call a group homogeneous if for each wavelength inside of it we will have the same number of photons and all with the same intensity. Let's see now what happens when a single photon hits an object. When it strikes its external surface in the incident point, according with the angle between the photon and the perpendicular line to the surface in that point, the material and its wavelength, it may react in different ways. When the incident angle is larger than what we will call the limit angle, independently from the material and its wavelength, our photon will bounce and leave. When the incident angle is lower than the limit angle, the photon will behave as a wave and it will split in two photons. One that we will call the reflected wave that will still bounce and leave, and another that we will call the refracted wave that will actually penetrate the surface getting inside the object. According to the material, the intensity of the reflected and refracted wave can be different. They mostly depend on the wavelength of the photon and on the incident angle. The angle of the reflected photon is exactly the opposite of the incident angle, and it depends on the perpendicular line in the incident point, while the angle of the refracted photon depends on the angle with the perpendicular line, but also on the type of material of our object. The refracted wave, while it runs inside the object, bit by bit it loses part of its energy, decreasing its intensity. We are going to say that the material is very opaque if the run of the refracted photon is very short and it gets completely absorbed. In this case, its carried energy is transferred to the object, raising its temperature. we're gonna say that the material is really transparent if the refracted wave will run inside for the whole thickness of the object, and it will get out from the other side with a very small attenuation, therefore losing a small quantity of energy. Of course, these are the two extremes of a very wide range of possibilities, so we can find materials very opaque, semi-transparent, transparent, and very transparent. Now that we know how a single photon behaves when it strikes an object, let's see what happens when a white light flux hits the same object. In this case, we have a large number of different photons that strike it on an equally large number of incident points. Every single reflected wave will bounce in the direction of the opposite angle between the photon and the perpendicular line to the surface in the incident point. If the external surface is flat and very smooth, all the waves will bounce and leave the object going in the same direction. On the other side, if the external surface is rough, in each incident point, the perpendicular line to the surface has a different direction, and consequentially, all the reflected waves will go in different direction. In this case, we will say that the white light flux gets diffused. The same thing happened to the refracted waves. If the external surface is very smooth, all the photons of our flux will be refracted in the same direction. If the external surface is rough, the white light flux will be diffused inside the object. Let's see now what happened to the part of the white light flux that missed the object. In this case, it's the corpuscular theory that explains better its behavior. Since every mass generates a gravitational field around it, when the corpuscles of the light get inside the object gravitational field, even if they don't touch it, they are subject to a force that pulls them in the object direction, changing their trajectories. We're going to call this phenomenon diffraction, and the part of the flux that changes its trajectory the diffracted flux. So far, we have talked about what happens when a flux strikes an object with a flat external surface. But in the real world, it isn't always like this. So let's say, for example, that our flux strikes an object with an irregular shape. If the external surface is rough, in every point its perpendicular line has a different direction. So also in this case, the reflected flux gets diffused. But even if our object has a very smooth surface, the perpendicular line in each incident point has a different direction as well. So also in this case, the reflected photons bounce in different directions. But this time, according with the shape, we're going to have areas where the reflected light flux converge and other areas where it diverge. And in case of transparent materials, this also happens to the light flux that gets out from the other side. We are going to call these caustic effects. We don't want to spend too much time on this subject because it's pretty complex and we don't really need it, except for these nice games of light that we get in our painting if we decide to paint them. And with this last consideration, we have concluded our discussion on the light. If you enjoyed this video, we will really appreciate if you could click on like and subscribe to our channel. It will also help us very much if you could leave a comment. Thank you for watching this video and see you in the next one.